Okay, so I'm going to explain empirical formula to you. And an empirical formula is the simplest whole number ratio of the moles of each element. So when we look at a formula like N2O4, that's the molecular formula. And then like reducing a fraction, what's the simplest ratio between the nitrogen and the oxygen? That's like dividing through by 2. So it's 1 N to 2 O's. We can think of that as atoms or as moles. So there's 1 atom of nitrogen for every 2 atoms of oxygen, or there's 1 mole of nitrogen for every 2 moles of nitrogen. Okay, so empirical formula is the simplest ratio. Sometimes the molecular formula and the empirical formula are the same. Like CO2, it can't be reduced down anymore. That's just the molecular formula and the empirical formula, H2O, N2O5. Okay, so the difference between molecular formula, that's how it naturally exists, that's how it really is. It could be that the empirical formula and the molecular formula are the same, or it could be that the empirical formula is like reducing down the molecular formula. So in this example, what's the empirical formula for C2H6O2? Well, we can divide all of those by 2. So the empirical formula would be CH3O. Okay, so this is the molecular formula. This is the empirical formula. For the second one, Ba3PO42, I can't reduce that down. There's no number I can divide through. So the empirical formula equals the molecular formula. Okay. So if we found a container of some compound and we wanted to figure out what it was, if we analyze it, we can figure out how many grams of the different elements are in there. If you've ever watched something like NCIS or CSI, they have machines. You can throw the sample into the machine. It can tell them exactly what element is in there in either by percent or by grams. And from that, you can figure out what the simplest mole ratio is of the substance. That's called the empirical formula. So our sample problem, we have a compound. It was found to contain 2.82 grams of sodium, 4.35 grams of chlorine, and 7.83 grams of oxygen. We want to determine its empirical formula. So just like we did in the lab when we were trying to figure out what was the ratio between the magnesium sulfate and the water, we do the same thing with these elements. How do they relate to each other in moles? So we just divide each one by its molar mass. That's how we always get from grams to moles. So for sodium, its molar mass is 22.99. I'm getting that right off the periodic table. For chlorine, the molar mass is 35.45, and for oxygen, it is 16.0. So divide each one by its molar mass. That gives you mole amounts. Okay, so that's always step 1 to do empirical formula. Divide by the molar mass. You have to compare mole amounts. You cannot compare gram amounts. Okay, step 2 is then divide each one by the smallest. Okay, divide each one by the smallest number. So looking at those numbers that we just had, 0.123, 0.123, and 0.489, the smallest, 2 of them match, but the smallest is 0.123. So divide each one of those mole amounts by 0.123, okay? Because we need whole numbers. You can't have a formula like this, Na.123, Cl.123. We need like Na1, Cl1, okay? So that's why we're dividing by the smallest to make those whole numbers. And when we divide by that, that one equals 1, that one equals 1, that one equals 3.98, which that's close enough to 4 that we can round that to 4. So then our formula is NaClO4. That's the empirical formula. That's the simplest ratio of the elements to each other by calculating their moles. If we wanted to know the empirical mass of the formula, we will just add up how many of each there are. If we want to name that formula, remember our polyatomic ion, ClO4 minus 1 is perchlorate. So this would be called sodium perchlorate. Okay, and the empirical mass is just adding up the molar masses of each of those elements. So again, sodium's 23, chlorine's 35.45, oxygen 16, and there's 4 of them. So adding those up, the empirical mass comes out to be 122.45. Okay, let's try another one. Determine the empirical formula and molecular formula. We're going to add one more thing for a compound that's found to contain 43.64% phosphorus and 56.36% oxygen by mass. Sometimes you're given the amounts as percents instead of as grams. It doesn't matter. You can just make those grams, because if we had 100 grams of the compound, we would have 43.64 grams of phosphorus and 56.36 grams of oxygen. So I just immediately just make those percents grams. Okay, treat them as grams. All we care about is the ratio of them to each other. It doesn't matter how much of the compound we have. Always 43.64% of it will be phosphorus. Okay, so just make those percents grams, and we're going to get the ratio. So just like before, you can't do anything with grams. You have to be in moles. So we have to convert from grams to moles with molar mass. So we divide each one by its molar mass. We get moles. But those aren't nice whole numbers. That's not, and you can't just round here. You have to divide by the smallest. Okay, that is always the next step. When you're in moles, then divide by the smallest. So looking at the two numbers, one of them is 1.409, one of them's that, so I'm going to divide each one of them by 1.409. Okay, and at this point, I hope to get whole numbers, but if I don't get whole numbers, I can't just round after I divide. There's one extra step here. So the first step's always divide by the molar mass. The second step's always divide by the smallest. Then I'm going to get numbers here. In this case, I'm going to get 1, and in this case, I'm going to get 2.5. This is where you have one extra step if you end up with a decimal. If it's 0.1, so if this would have been 2.1, you can just round that to 2. If it would have been 2.9, you can just round that to 3. But when it's 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, you have to multiply by a number to make that within 1/10 of a whole number or a whole number. So in this case, a 1 to 2.5, 2.5, I can multiply by 2, and that'll make it 5, and that's my whole number. But if I do multiplication to this one, I have to do multiplication to this one, okay? They are our ratio. So when I multiply them both by 2, that becomes 5, and that becomes 2. So I end up with 2 phosphoruses and 5 oxygens. Okay, so again, always divide by molar mass, then divide by the smallest. If I don't get whole numbers, or if it's not within 1/10 of a whole number, you can't just round. You have to multiply them by numbers to make them whole numbers. So this one comes out to be again, 1 to 2.5, so multiplying both by 2, I get P2O5. Okay, that's the empirical formula. So what would be the empirical mass of that? 2 phosphoruses. I look up the molar mass of phosphorus, it's 30.97, and I have 5 oxygens, 5 times 16, and I add those together, and I get 141.9 is my empirical mass. Okay, well, what does that mean? Well, back in the beginning of the problem, it told us that the molar mass is 283.88. So if the empirical mass is not the same as the molar mass, then that means I don't have the formula of the compound yet, which is called the molecular formula. I only have the empirical formula. So my last thing to do then is to divide sorry, I'm having a little difficulty here. Divide by the molar mass, sorry, this is not right here, by the empirical mass. Okay, so the molar mass was given, again, back here in the beginning of the problem, it said it was 283.88. So when I just found the empirical mass, I will divide that 283.88 by the empirical mass, 141.9. And that will give me a whole number. If I don't get a whole number here, then I did something wrong and my empirical mass was wrong. Okay, so the molar mass divided by the empirical mass has to give a whole number. Sometimes they'll be equal. Sometimes the molar mass equals the empirical mass, and then we were done. So if we were told the molar mass was 142, then when we divide 142 by 141.9, it's 1. So that tells us the molecular formula is equal to the empirical formula. But if the molar mass is bigger, then when we divide, we're going to get a whole number. We need to get a whole number. In this case, 2. So that means we multiply that 2 by our empirical formula. So the molecular formula then is P4O10. Okay, so I'm taking that empirical formula and I'm multiplying it by 2. Okay, so that's the extra step to go from empirical formula to molecular formula. All right, let's look at a few more examples. If we were told that the empirical formula was CH2O, okay, we solve for that, we get CH2O. When we add up that empirical mass, we'll have 1 carbon, which is 12, plus 2 hydrogens, which is 2, plus an oxygen, which is 16. So that's 14, so that's 30. If then separately we're told the molar mass is 120 grams per mole, then we will always divide molar mass by empirical mass, and we have to get a whole number. Okay, so molar mass divided by empirical mass. So if the molar mass is 120, the empirical mass is 30, that comes out to be 4. So then that's the number we multiply the empirical formula by. Okay, so this was the empirical formula that I just made up like you would get it in a problem. And so we multiply that by 4. So we would get C4H8O4 would be the molecular formula. The molecular formula has to be a multiple of the empirical formula. Okay, so back at the beginning, if you're given data for each amount of an element, whether it's percent or gram, first step, divide by molar mass. You need a mole ratio. Then you need those to be whole numbers. So divide by the smallest. That automatically gets one of them to be 1, and then whatever the other ones were. If those aren't all whole numbers right there, you have to multiply through by a number to make it a whole number. And that's where sometimes when you've divided through, you might get 1 to end in 0.1, okay? And that you can just round down. So if when you divide it by the smallest, if it ends in 0.1, just round it. If it ends in 0.2, we need to get it up to a number that ends in 0, 1, or 9, so we can just round it off. So if, when we've divided by the smallest, if we get a number that's like 4.2 for one of them, that means we have to multiply all of them by 5, because 5 times 2 is 10, and that ends in 0. Okay. If one of them ends in 0.3, we have to multiply by 3. If one of them ends in 0.4, we have to multiply them all by 5. If one of them ends in 0.5, like we just had, we multiply them by 2. Okay, so we're getting to a number that ends in either 0, 1, or 9, because when it ends in those 0, 1, or 9, okay, that's close enough to a whole number. Okay, so if it ended in 0.6, we have to multiply it by 5. If it ends in 0.7, we have to multiply them all by 3. If it ends in 0.8, we multiply by 5. And then if it ends in 0.9, we can round. Okay, so this is at the step where we've divided by the smallest, but they're not all whole numbers or within 1/10 of a whole number. Okay, so that was the extra step sometimes for empirical formula in our second example. Okay, so to get the empirical formula, they need to be whole number ratios. And then after you have empirical formula, you can get molecular formula. This way, your molar mass divided by the empirical mass needs to give you a whole number. Okay, so there's 2 different cases where you have to have a whole number. When you're getting the empirical formula, and then if you didn't, that's when you're multiplying by these. And then when you divide molar mass by empirical mass, that's going to have to give you a whole number too. Okay. So try those problems on the other paper.